Hi, this is Tej Arora. I'm an AWS Certified Solutions Architect Associate. In the AWS Quick Learn series, I will cover AWS services and features in short videos. These videos will provide a quick 360-degree coverage of a service or feature. They are suitable for those preparing for an exam or an interview or just want to refresh their knowledge. In this video, I will cover VPC, the Virtual Private Cloud Service. Let us begin with an introduction. So what is VPC? It stands for Virtual Private Cloud. Using it, you can create your own piece of AWS Cloud. So it is an isolated, customizable network in the AWS Cloud. So a VPC is a logical boundary with its own IP address spaces, its own subnets, routers, and gateways. Note that different customers who create VPCs can use the same private IP address ranges. So what does a VPC contain? It contains AWS resources and applications that communicate within the VPC and outside the VPC. So examples of what a VPC can contain are EC2 instances, RDS instances, elastic load balancers, ECS clusters, and so on. In a VPC, you can create a custom topology that includes a variety of publicly visible subnets and private subnets. VPC gives you the power to control traffic and access to resources and applications, and the mechanisms are security groups at the EC2 instance level and RDS instance levels. NACLs or network access control lists control access to a subnet, and IAM policies can be used to control access at the VPC level. So policies can have conditions that specify a VPC that's allowed. Now, what would you use a VPC for? You can use it to host websites and multi-tier applications. And in this multi-tier architecture, you can isolate backend tiers such as databases from public access by putting them in a private subnet. So you can use VPC to build a disaster recovery site for your on-premise data centers. You can also extend your on-premise corporate network into the cloud using VPN, virtual private networks. Now let's look at the key artifacts or resources and concepts associated with VPC. There's a lot of different resource types and concepts. So what I'm going to do is start with the diagram, and after I discuss all of these, I'll come back to the diagram. I found VPC to be one of the more difficult services to understand because of the variety of resources and concepts associated with it. So hopefully this diagram helps get a easier and clearer understanding. I'll start with a very quick high-level overview. I know this diagram is a little busy and it can get confusing. I won't go into every little detail. So to begin with, this box is the AWS Cloud. It contains multiple regions. A region contains multiple availability zones, and a VPC spans multiple availability zones, but it's limited to a region. A VPC can contain multiple subnets. In this diagram, I've just showed for illustration a public subnet and a private subnet. These subnets can contain instances, and note that a VPC is associated with an address range that's denoted by this. I'll talk more about this later. And within this address range, you can allocate sub-ranges to the subnets. There's various kinds of gateways: NAT gateway, internet gateway, virtual private gateway, so on, that we will cover more in detail later. But note that when you create a VPC, these are the attributes that it's created with. So there is a default security group that's created, and by default, it allows all outbound traffic and allows inbound traffic only from the same security group. Note that the default security group of a VPC cannot be changed or deleted. You can create additional security groups and configure them. Besides the security group, a VPC has a route table called the main route table. By default, this route table only contains VPC local routes, and a VPC is also associated with a default network access control list, which allows everything. You can create additional route tables and NACLs, but these are what a VPC is born with. And note that a subnet in a VPC inherits the route table and the NACL. In other words, it's associated with the main route table and the default NACL. But you can always create a new route table and a new NACL and associate with each subnet. Now, one of the key use cases is extending a corporate network and making AWS VPC a part of that network. So there's several mechanisms to do that. One is through VPN connectivity and the other is called Direct Connect. So let's go back now to discussing the artifacts and concepts. Let's start with IP address. There's two kinds of IP addresses, private and public. A private IP address, it can be reached directly from within the VPC. It cannot be reached from outside the VPC, with a couple of exceptions. When two VPCs are paired, they can access each other's private IP addresses. And in the case of a VPN connection between a corporate network and AWS, the private IPs can be reached from the corporate network. An EC2 instance, when created, has a primary private IP that can be assigned either by the user or the system, and that IP has to come from the subnet range. Basically, it has to be an unused IP. This primary private IP cannot be unassigned for the lifetime of the instance. There's also a few secondary private IPs. These can be assigned and unassigned anytime by the user. Public IPs can be reached from inside the VPC and outside, including from the internet. A public IP is assigned to an instance by the system from a pool of IPs. There's a specific public IP called an elastic IP. It is basically a portable public IP. It can be reserved by the user and it can be attached to or detached from the network interfaces by a user. Network interfaces, you can loosely understand that as an EC2 instance. So an elastic IP can be attached and detached from an EC2 instance. If the elastic IP is attached to the primary network interface of an instance, the public IP, if allocated, is released. And when it's detached from the primary network interface, the public IP is reassigned to the instance. If the elastic IP is reserved by a user, but it's not attached to a running instance, during that time, there is an hourly charge for the elastic IP. Keep that in mind. Now, IP addresses are of two different lengths, an IPv4 and an IPv6 IP address. V4 addresses are 32-bit long, and since there's only 2 to the 32-bit addresses that can be created, so there is a limited number of addresses and we are running out of these. As a result, a new standard was created called IPv6, which supports 128-bit addresses. Support for IPv6 is there in AWS and in many systems, but it's not as commonly used as IPv4. Now, an IP address range. Why do we need a range? So when you create a VPC or a subnet, you need to specify an address range, which is basically a set of IPs that can be used. Note that there are 3 IP address ranges that are reserved by IANA for private IPs. So whenever an address is in one of these forms, it's considered a private IP address because it has been designated by a standards body. I will discuss this representation in a moment. So how is a range of IP addresses represented? What is used is a CIDR or a CIDR. It stands for classless interdomain routing. So to give you a couple of examples, I had mentioned that /16 is the largest IP address range you can use for an AWS VPC. So what that means is /16 means that the first 16 bytes are a mask and unchanged. The remaining 32 minus 16 bits can be changed. So this representation stands for an address range whose first IP address is 10.0.0.0 and the last address is 10.0.255.25. Note that 10.0, the first 16 bits, is a mask and cannot change. Let's take another example. This one, /32, means 32 bits are a mask and the remaining bits, which is 0 in this case, can be changed. So what it means is that all 32 bits are fixed, which means this range has only one address, and that is 182.83.43.30. Now, Amazon recently introduced a concept called a prefix list. It's essentially a set of one or more CIDRs or IP address ranges. Now, this prefix list can be either managed by AWS or created by the customer. These prefix lists can be referenced in route tables and in security groups. Note that even CIDRs can be used in route tables and security groups. Prefix list adds support for a list of CIDR. Now, NACL, which is Network Access Control List, and security group are both mechanisms to control access. So let's look at their properties and the differences between them. So let me first go over an ACL and then I'll talk about a security group and you can see the differences. So an ACL is used to control inbound and outbound traffic for a subnet. It is a set of rules, inbound rules and outbound rules. It's basically a virtual firewall. So the rule looks like this. It has a rule number. There's a source destination CIDR, there's a protocol, a port range, and whether to allow or deny the access. Note that there is one rule, it's a special rule, which is always built in an ACL, and it cannot be changed. The rule number is the asterisk sign. And this CIDR means all IPs, protocol all, port range all, and action is deny. So essentially, this special rule is in place. In case no rule matches, then this is the final rule that applies. A subnet can have only one NACL, but a NACL can be associated with multiple subnets. A new NACL has no rules, nothing is allowed in or out, except for the special rule, which pretty much implements this. A rule can allow or deny traffic. A NACL is considered stateless. Inbound traffic depends only on inbound rules. Outbound traffic depends only on outbound rules. And this will make more sense when we discuss the stateful model of security groups. Now, each rule has a rule number, and the rules are processed in the order of the number. A NACL lives in the scope of a VPC. A NACL in one VPC cannot be referenced in another VPC. Note that a NACL cannot control traffic to or from link local IPs represented by this CIDR or AWS reserved IPs. And note that all the instances in a subnet, all the EC2 instances, a NACL automatically applies to them. Now let's talk about security groups. Security group also controls inbound and outbound traffic for network interfaces, or you can loosely say traffic for EC2 and RDS instances. It has a set of inbound rules and outbound rules. It's also a virtual firewall. The rule looks like this: a source destination CIDR, a protocol, and a port range. All rules are allow by default. Hence, there is no other parameter here like a NACL rule has. Note that a source destination can be an IP CIDR or it can be a security group ID, which means a security group is not just a firewall of rules, it also indicates membership. An instance can have many security groups. A subnet can have only one NACL. A security group that is created, it begins with no inbound rules, which means nothing is allowed in, and one outbound rule that allows all traffic out. Also note that when you create a VPC, its default security group has one inbound rule to allow traffic from instances within the security group. But if you were to create a security group on your own, it has no inbound rules. I mentioned all rules are allowed by default. Now a security group is stateful, which means the inbound traffic is everything that's allowed by the inbound rules plus any response to outbound traffic that is allowed. Similarly, outbound traffic is all the traffic that's allowed by outbound rules plus the response from allowed incoming traffic. There are no rule numbers for security groups. Every rule is processed before traffic is allowed or denied. A security group lives in the scope of a VPC just like NAC. It cannot control traffic from link local IPs or reserved IPs just like NACLs. And note that a security group applies only to a specific instance to which it is attached, as compared with a NACL, which automatically applies control to all the instances in a subnet. So if you wanted a central control on all instances in a subnet, an additional layer of control, you can use a NACL in addition to security groups. Now that we've covered NACLs and security groups, let's look at the concept of ephemeral ports. Now, when a source connects to a destination, let's say at port 80, that source connects from an ephemeral port. So from ephemeral port to port 80, that's the connection. Now an ephemeral port is a temporary port that's assigned from a pool and it's returned to the pool when done. The pool consists of port numbers that are in a certain range that depends on the source. For example, this is the range used on Linux. This is the range that AWS, load balancer and NAT gateway uses. So it depends. It's important to know about ephemeral ports when setting rules for a NACL. Remember that outbound rules need to be set for incoming traffic on standard ports like 80. Because remember, it's coming from an ephemeral port and the response will go back to the ephemeral port. So the outbound rules should allow it. Similarly, when there is outgoing traffic to standard ports like 80, the response coming back will come to an ephemeral port and the inbound rules need to allow that. Now, Elastic Network Interface, or an ENI, what is that? You probably are aware that home PCs have what is called a NIC, a network interface card. And ENI is basically like a NIC, except it's virtual. It's referred to as a VNIC. So it's a virtual network interface. And an ENI has these attributes. It has a primary private IP. It has one or more secondary private IPs. Optionally, it has a public IP and an elastic IP per private IP. So elastic IPs can be assigned per private IP to an instance. It is associated with one or more security groups. It has a MAC address and there is a flag to check source and destination. This flag basically checks if the traffic is from this source or to this destination. An EC2 instance can check this to discard traffic that has not originated from it or is not destined to it. Now, where do we use ENIs? So an EC2 instance has a default or a primary ENI. It cannot be detached from the instance and it's assigned a private IP from the subnet's address space, which comes from the VPC's address space. This is also commonly referred to as ETH0 or ETH0. An EC2 instance also has one or more additional ENIs. They can be detached from the instance and they can be reattached to another instance. And when you reattach an ENI to another instance, the traffic goes with it. So traffic is destined to an ENI, and if the ENI goes to another instance, then the traffic goes to that instance. So why do we need multiple ENIs for an instance? If you want to create a dual homed instance that is listening on different subnets, running different applications, that's one use case. The other is it's some form of redundancy, which gives high availability. So if one ENI were to have some issues or problems, you can have the other ENI still serving traffic. Now let's look at routes, route tables, and routers. So this is a route table. It contains two routes in this table. A route table essentially is a table of rules, and each rule is a route. And note that a route table is associated with a subnet or a gateway. Now the route, each rule specifies how to direct traffic for a certain destination. So traffic to a certain destination is represented by a CIDR, and where it goes is called a target. And target may be local, it can be a gateway, or it can also be an ENI. What a router does is it uses a route table and routes traffic. And note that in a route table, there have to be separate rules for IPv4 traffic and IPv6 traffic. In this diagram, I've only shown IPv4 CIDRs. A subnet lives in a VPC. It is associated with a CIDR, and keep in mind that every CIDR that's assigned to a subnet, 5 addresses from the CIDR block are reserved by AWS. So the 0, 1, 2, and 3 and the 255 address, these are all reserved for various purposes. So when you assign a CIDR block to a subnet, keep this in mind. And note that traffic from these reserved IPs cannot be controlled by NACLs and security groups. Now a subnet is associated with one NACL. It can be a custom NACL or the VPC's default NACL, but also note that one NACL can be associated with many subnets. It has one route table, which can be a custom route table or the VPC's main route table. But also note that one route table can be associated with many subnets. A subnet also has a flag called the assigned public IP flag. It's false by default, but it is set to true for default subnets that are set up in a default VPC. We'll talk more about default VPC in a few minutes. Now, if this flag is true, any network interface that is created within the subnet, which happens when an EC2 instance is created, that network interface is assigned a public IP. That's what the flag means. So it governs the assignment of a public IP to instances created in the subnet. Now, what is a public subnet? What it means is that traffic from the subnet has a route to the internet, which means the subnet is associated with a route table that has a rule leading to the internet gateway, with target as the internet gateway. Note that if a subnet has assigned public IP flag to true, it doesn't make it a public subnet. It also needs to have a route to the internet. Now, in a default VPC, the default subnets that are created are public subnets. Now, there's also a VPN-only subnet. If the traffic from the subnet has a route to a virtual private gateway, but no route to the internet gateway. When you create a brand new subnet, these are the defaults it's born with. It inherits the VPC's default NACL, it inherits the VPC's main route table, and the assigned public IP is set to false. Now let's look at gateways. Gateways play an important role in routing traffic to different destinations. And these are the different kinds of gateways. So an internet gateway, as the name suggests, enables communication between VPC resources and the internet. A virtual private gateway, it enables communications between a VPC and a corporate data center over a private channel. And the options for connecting to a virtual private gateway are a VPN connection from the corporate data center or a direct connect connection from the corporate data center. A NAT gateway essentially is a bridge between a private subnet and the internet. Now note that instances in a private subnet by default do not have access to the internet. But what if your EC2 instance needs to download a package during installation? So it does need to have a path to the internet, but we don't want it to be accessed from the internet. So that's when a NAT gateway comes in. So to the outside world, the NAT appears like a public IP, and on the inside, many different private IPs from the private subnet can connect to the internet through the NAT. So what NAT does is it maintains a mapping table that maps traffic from these multiple private IPs to the internet, so that when a response comes back, it knows how to route it. NAT uses an elastic IP and it needs to connect to the internet through an internet gateway. For availability reasons, it's recommended that you create a NAT gateway in each availability zone that you use. Now, besides a NAT gateway, if you wanted, you can roll your own EC2 instance that performs NAT functions, and it's typically called a NAT instance. But the reason a NAT gateway is recommended is because it's highly scalable and available. Now, how do you create a NAT instance? So you create an EC2 instance from a special AMI that supports NAT. You disable the source destination check attribute for the instance because we don't want the NAT to drop traffic that is not destined to the NAT or originates from the NAT. You assign a public IP or elastic IP to that instance. You put it in a public subnet and you have a route from the private subnet to this instance, and you associate the instance with a security group that allows traffic from the private subnet. Now, an egress only internet gateway specifically for IPv6 traffic is essentially the equivalent of a NAT gateway, but for IPv6 traffic. Finally, a transit gateway. Now, we haven't discussed VPC peering yet, but essentially VPC peering is between two VPCs. It's point to point. So if you have a lot of VPCs to peer, then a transit gateway is a more flexible solution. What you can do is you can attach a variety of entities to a transit gateway. You can attach VPCs, virtual private gateways, direct connect gateways, and other transit gateways to it, which is like transit gateway peering. And it basically acts like a router for traffic across all these different entities that it's attached to. Now, VPC. So when you create a VPC, you can assign a primary CIDR, which is as big as /16 and as small as /28. And once it's created, you can assign 4 secondary IP blocks or CIDRs with similar limits. Note that a VPC spans all availability zones in a region, and the defaults for a newly created VPC are there is a main route table which has a route rule to allow traffic within the VPC. It has a default NACL which allows all inbound and all outbound. It has a default security group which allows all outbound traffic and inbound all traffic from the same security group. And it has no gateways attached to it. So if you wanted an internet gateway to route your traffic to the internet, you need to create it and attach it to the VPC. Now I mentioned the default VPC. Default VPC is just a regular VPC, except it's created in advance for every account. Creating a VPC involves a number of steps. A lot of different resources have to be created and associated. So AWS creates one for every account so that the user doesn't have to go through all these steps. And this default VPC has an internet gateway created and attached to it. It has a default subnet in every availability zone in the region in which it's created. All the subnets have the assigned public IP flag set to true, which means an instance created in these subnets will get a public IP assigned. All the default subnets are public, which means there is a route to the internet from the subnet, which means the route table associated with these subnets has a route to the internet. And that is the main route table that's associated with the VPC. Now, when you launch an EC2 instance without specifying a subnet, they go into the default VPC. But you can have your own VPC with its own subnets, and you can launch instances in those subnets. When EC2 instances are launched in a default subnet, they get a private IP and a public IP and can communicate with the internet. A bastion. Now, if you have to SSH to an instance that's in a private subnet, how do you do that? Because private subnets by default are not accessible from the internet. That's where a bastion comes in. So you can SSH to a bastion host, which lives in a public subnet. And then from there, you can hop to the private subnet instance, assuming you've set up access to the private subnet from the public subnet. A bastion is basically a host which has very little functionality on it. It's a security hardened host, and its only job is to be a hopping point to log into private subnet instances. This keeps it simple and secure. Having discussed all these concepts, let's look at the EC2 internet traffic and EC2 internet connectivity. Now, how do you determine if an EC2 instance has internet connect? So if it has a public IP or an assigned elastic IP and it has a route to the internet gateway, which means its subnet is associated with a route table that has a route to the internet gateway, then yes, it has inbound and outbound access. If it has a public IP or assigned elastic IP but no route to the internet gateway, let's see if it has a route to a NAT gateway or an instance. If it does, there is outbound access on. If it has no route to the internet gateway or to the NAT gateway, then there is no internet access. Now, how does traffic flow between EC2 instances that have public IPs? If the instances are in the same region, the traffic stays within the AWS net. If the instances are across two different regions, but the VPCs they live in are peered, then again the traffic stays within the AWS net. Otherwise, if there is no VPC peering, the traffic may traverse the internet. Now that we've seen all the different artifacts and concepts associated with VPC, let's go back to the picture and refresh our understanding of all these different concepts. So the cloud with multiple regions, VPC lives in a region and it can have multiple subnets in each availability zone. A subnet is within the scope of an availability zone. A VPC has a CIDR, a primary CIDR and additional secondary CIDRs, which define the address ranges that can be used for elements in the VPC. Similarly, a subnet has a CIDR range, a CIDR, which can be used by instances in the subnet. And a subnet is associated with one route table and one NACL. But if you don't explicitly assign a route table and a NACL, subnets inherit them from the VPC. And the VPC is associated with a default security group which cannot be changed, and a main route table and a default NACL. Routers help route traffic as defined in route tables. Route tables are associated with subnets, and so when instance traffic has to be routed, these route tables are used by the router. Now let's take a look at NAT gateways. So here's a private subnet for this instance to connect out to the internet. It needs a NAT gateway, but note that traffic from outside the internet cannot directly connect to these instances, but it can connect to instances here. And from a corporate network, there's two ways to connect to AWS. One is through a VPN connection and another is through a direct connection. We'll talk a little more about these later. And a direct connect connection can be used to access a VPC or AWS services like S3 and so on. A direct connection is a private, dedicated physical connection which provides very high bandwidth and reliable performance, whereas a VPN connection is a virtual private connection over the internet. It can be set up very quickly, but it doesn't provide bandwidth as high as a direct connection. A virtual private gateway facilitates connectivity with the corporate network. An internet gateway facilitates connectivity to and from the internet. So instances to the internet and internet to the instances. So VPC endpoint is a special feature which I'll talk more about. Traffic between the instance and that service remains within the AWS network and does not go out to the internet. Now let's look at some of the features supported by VPC. So VPC peering. It's a connection that enables private traffic between two VPCs using private IP addresses. It appears as if both VPCs are just one VPC. Note that the peering VPCs must have non-overlapping IP address ranges. And there is no support for transitive peering, which means if VPC A is peered to B and B is peered to C, it does not imply that VPC A is peered to VPC C. It has to be set up explicitly. Note that peering works across VPCs in different regions and across different accounts. VPC endpoint is a feature that enables traffic from the VPC to AWS cloud services without using an internet gateway or a NAT or VPN or direct connect. So what are the services that a VPC can reach through this direct access and fast access mechanism? Oh, they can be services provided by AWS. They can be services hosted by other accounts, and you can create your own VPC endpoint hosted service as well that other VPCs can access. It can be marketplace partner services. So when a VPC endpoint is used to send traffic, that traffic stays within the AWS network. It does not go out to the internet. So if you access, let's say, an S3 service using a VPC endpoint, even though that S3 service is publicly visible, your traffic does not go out to the internet to reach S3. Instances that connect to VPC endpoints do not need a public IP. And remember, they do not need an internet gateway or a NAT or a VPN or direct connect connection. There's two types of VPC endpoints: interface VPC endpoints and gateway VPC endpoints. Now, gateway VPC endpoints are well-known and advertised endpoints. And like any other gateway, these endpoints can be incorporated as a target in a route table. At this moment, only S3 and DynamoDB have gateway VPC endpoints available. So sending traffic to S3 is simply a matter of putting its gateway VPC endpoint into the route table. Now the interface VPC endpoints are user created, and when you create one, what happens is an ENI is created with the private IP from the subnet CIDR, and this private IP is basically the virtual entry point for the destination service. And you should ensure that the subnet NACLs permit traffic to that interface and from that interface. And also make sure that the security group associated with the ENI permits traffic as well. Now, remember that endpoint traffic cannot cross regions, but it can connect an AWS VPC to an on-premises data center or a corporate data center using VPN or direct connect. So it cannot span regions, but it can reach an on-premise data center. Basically, between AWS and on-premise data center, VPC endpoint traffic can flow. And the AWS feature that enables VPC endpoints is called private link. And regardless of whether you use gateway endpoint or a VPC interface endpoint, you can have a resource policy attached to that endpoint to control access to the service. VPC has features to enable traffic inspection. So EC2 outbound traffic can be mirrored and inspected out of band. This feature is called traffic mirroring. The traffic that is mirrored can be sent to another EC2 instance or to a network load balancer. In addition to traffic mirroring, all VPC inbound and outbound traffic can be inspected by an inline appliance. Now, this traffic inspection is useful for analyzing threats, security threats, and for troubleshooting connectivity issues. Entire traffic payload is captured. Now, compared to another feature called VPC flow logs, where only metadata is captured, traffic inspection captures the entire packet payload. So it allows deeper analysis of your traffic. Now, VPC flow logs is another mechanism to inspect your traffic. So it captures IP traffic to and from all network interfaces in VPC, except traffic from reserved IP addresses and link local addresses. You can capture traffic at many levels for an entire VPC, for a specific subnet, or for a specific instance. This captured data, it can be pushed to S3 or CloudWatch to analyze it further to study the effectiveness of your access controls using NACLs and security groups. Note that VPC flow logs are captured out of band and there is absolutely no impact on network throughput or latency when you enable this. The flow logs are captured in records. A record is for a specific interval called the aggregation interval, and during that interval, what's captured is for every piece of traffic, the account ID, the interface ID, source destination IP, port, the protocol in use, the number of packets and bytes flowing, start and end time, firewall action, whether it allowed or denied, a VPC ID, subnet ID, region, and so on and so forth. So essentially, this is metadata relating to traffic flow. So a flow log is a set of flow log records, which is captured for a specific interval. And to reiterate, only metadata is captured versus the traffic mirroring feature where entire packet payload is captured. Now, the DNS hostnames feature, a VPC can be enabled for DNS hostnames. And what that means is when an instance is created in a VPC and it receives a public IP or an elastic IP, it automatically gets a DNS hostname. And these DNS hostnames, they resolve to a private IP within the VPC and a public IP outside. Now, as mentioned earlier, one of the biggest use cases of VPC is to extend corporate networks, corporate data center networks to AWS. So the connectivity to remote networks is a key feature. It comes in two forms: a direct connect connection and a VPN connect. So let's look at direct connect. It's a dedicated physical network connection between the remote network and AWS cloud. The traffic flows not on the internet, but on the dedicated connection. It provides fast, predictable network performance and high bandwidth network. It allows multiple virtual interfaces to be created, and each interface, you can configure it to access services using public services in AWS, such as S3, or using private IPs in a specific VPC. So you have the flexibility to use Direct Connect for accessing public AWS services or private IPs within a VPC, or both. A VPN, on the other hand, is not a physical connection. It's a virtual private connection between the remote network and AWS cloud, and it uses the internet and not a dedicated physical connection. Now, there's 4 types of VPN connections: AWS site-to-site VPN, AWS client VPN, a VPN Cloud Hub, and a third-party VPN appliance. So a site-to-site VPN connection essentially sets up a secure VPN connection between the VPC in AWS and a remote network. What you have to do is, on the AWS side, you have to set up a virtual private gateway or a transit gateway. And when you do that, 2 endpoints are created in the virtual private gateway for failover. On the remote network side, the customer gateway has to be set up to facilitate a site-to-site VPN connect. What a client VPN provides is you can use an open VPN-based VPN client. You need to set up a secure endpoint in the AWS VPC or your remote network, or both. Essentially, what the VPN client does is helps connect to either AWS or the remote net, and it establishes a VPN session. Cloud Hub is simply a case of multiple remote networks that are connecting to AWS. So essentially, it's a multiple site-to-site VPN connections via the virtual private gateway. You can also use your own VPN appliance. This is a self-managed solution. You can run this appliance on an EC2 instance in your VPC and use the internet gateway to establish your VPN connection, as opposed to a virtual private gateway that AWS manages for you, and you can use that to set up a VPN connection via these mechanisms. Now, if you compare Direct Connect and VPN, VPN can be established very quickly in minutes, and it uses the internet. It's low to medium bandwidth, and the traffic is encrypted by IPsec. Whereas Direct Connect is a dedicated private connection, takes a while to set it up, it bypasses the internet, and it's great for high bandwidth requirements. Let's look at some of the limits, also known as, well, it's known as quotas now. It used to be called as limits. Just a few of them quickly. So you can have 5 VPCs per region, and in a VPC you can have 200 subnets and 200 NACLs, and per NACL you can have 20 rules, and you can have 200 route tables per VPC and 50 rules per route table. You can have 2,500 security groups in a region, and the number of inbound outbound rules per security group is 60. The number of CIDR blocks, IPv4 CIDR blocks per VPC is 5, 1 primary and 4 additional, 4 secondary, and the number of IPv6 CIDR blocks is limited to 1, and you can have in an availability zone up to 5 NAT gateways. Now, some of the elements that affect pricing include, so site-to-site VPN connection, there is a per hour charge for the connection, and data transfer out of AWS is charged. And there's also, if you use client VPN to connect to the remote network or to AWS network, there is a per hour charge for the connection when it's active. And when VPC endpoint is used, there's a per hour charge for the endpoint and data transfer through the endpoint in both directions. If you use traffic mirroring, for every hour it's enabled, there is a charge. NAT gateways, if used, there's a per hour charge and data transfer charges in both directions. And there's, for direct connect, pricing is based on the number of ports connected, the bandwidth of each port, and the data transfers over the direct connect connection. So there is a port hour charge, and the port hour charge depends on the band. The only metrics, CloudWatch metrics published in VPC are NAT gateway metrics, and they include connection counts, the bytes and packets in and out, packets dropped, etc. In terms of VPC integration with other services, these are some of them. Now, IAM is integrated for access controls, using policies to VPC resources, such as VPC endpoints and subnets and so on. Now, EC2 is integrated with VPC because instances always are created in a VPC. That is the EC2 VPC instances, not the classic instance. RDS and ELB instances and ECS clusters are created in VPC, so they are integrated. Lambda functions can communicate with resources in a VPC. There's some integration there. And CloudWatch can be used as a destination for VPC flow logs. Now let's take a quick look at how VPC facilitates the 5 pillars of the well-architected framework. In terms of operational excellence, the traffic mirroring, the VPC flow logs feature, and the NAT gateway metrics facilitate troubleshooting of problems, and they allow analysis of security threats. In terms of security, VPC has 3 levels of security. So you can have private subnets to safeguard and isolate your backend resources that should not be exposed to the public. There's NACLs that control access to all instances in a subnet. And then there's security groups, which can be set up on a per instance basis and control access as well. Now, traffic inspection features helps discover threats and security holes. And also note that VPC is PSI DSS compliant. For supporting reliability, now traffic between availability zones and between regions, this is routed over AWS's private global network. And that network has an SLA of an hourly packet loss rate of less than 0.0001%, 99% of the time. That's pretty reliable. And VPC gives you a variety of connectivity options from VPC and to VPC. You can use VPC endpoints, gateways, route tables, and so on. And what this does is these multiple connectivity options assist with resiliency, and they give you flexibility to design your topology in a reliable way. And note that all the gateways that are provided by AWS, they are redundant and highly available. In terms of efficiency, VPC endpoints help keep traffic within the AWS network, and Direct Connect provides fast and private high bandwidth connectivity to AWS. There isn't anything on the cost management aspect in VPC. Thanks for watching the video. If you found it useful, please consider clicking on the like and subscribe buttons. If you can leave a comment about what you liked and what could improve, I would really appreciate that. Thanks again.